Now we could speak about the next one, the sign flag. The sign flag equals the most significant bit of the last result. You can actually think about it as a copy of the most significant bit. After every calculation, the sign flag is just a copy of the most significant bit. So actually the sign flag is 0 if the result is positive in the 2's complement representation, and it is 1 if the result is negative in the 2's complement representation. We can say those things because we have some idea about what is the 2's complement representation, but even if we didn't know about positive or negative numbers, it is still true that the sign flag equals the most significant bit of the last result of any calculation. Let's look at some examples. The first one, move EDX 0, just zeros EDX. I remind you that this instruction has no effect on the flags, because it is not a calculation. It is an instruction about data transfer. The next instruction is decrease EDX. It just decreases the value of EDX by 1, which should result in this number. We have 8 F's here. And so the sign flag is going to be 1. Why is that? Because the most significant bit of this number of EDX is 1. The processor can see that the result has a most significant bit of 1 and it copies it to the sign flag. Now let's look at a different example. This time we put 0 inside EDX and then we increase it by 1. So the result is going to be 1. And the sign flag is going to be 0. Why is that? Because the most significant bit of EDX is 0. You have to imagine that there are 7 leading hexadecimal zeros before this one. And so the highest bit is going to be 0. These are two contrasting examples. One for sign flag set to 1 and the other one of sign flag cleared to 0. The sign flag is also a pretty simple flag. It is very basic. It is just a copy of the most significant bit. So it could be pretty useful for you in many cases. The carry flag. The carry flag is a more sophisticated flag. At least more sophisticated than 0 and sign. It can actually understand unsigned addition and subtraction. And let us explain a bit about it. The carry flag is sent if the addition of two numbers causes a carry out of the most significant bits, or the leftmost bits. Let's look at an example to understand what was just said. We have those two instructions. The first one, move EAX 8Fs. This is actually the largest unsigned number that you could put inside EAX. And the next instruction adds 1 to EAX, which should result in EAX equals 0 because of the wraparound of 32 bits. In this example, the carry flag is going to be set to 1. How it looks like binary wise. We have EAX, which looks like this. It is made of all ones. We can see in the highest row the numbers of the bits. This is bit number 0 and this is bit number 31. And we add the number 1, which looks like this. All zeros beside the lowest bit, the lowest significant bit, which is 1. By addition, as you probably know by now, we get this number. We have this line here because inside our processor, in 32-bit protected mode, we can only store 32 bits inside the register. Only those bits are going to be the result, and this bit is just going to disappear somehow. So instead of disappearing, this bit is going to be put inside the carry flag. This could be pretty useful. You have another bit which is inside the flags register that stores this bit that usually disappears if you don't look inside the flags register. This bit actually have a bit of a deeper meaning when talking about unsigned addition. This bit tells you that the result you got adding two unsigned numbers is wrong. For example, here we added some two numbers which were both positive. They were non-zero. They actually had value. We added those two numbers and somehow, strangely, we got a result of 0, which is incorrect. Those are pretty large numbers. How come we added those two numbers and we only got 0? If we take a look inside the carry flag, we can see that it has the value of 1, which should give us a hint that something went wrong with our addition. Here we got a strange wraparound. We have this kind of wraparound, and the carry flag is the only way we have of knowing that it actually happened. If we didn't have the carry flag, we won't have enough information to know that a wraparound happened. Maybe to summarize, the carry flag actually understands unsigned addition or subtraction, and it can tell you if something went wrong when you added two unsigned numbers. Let's talk about subtraction. The carry flag is also set if the subtraction of two numbers requires a borrow from the most significant bits. For example, here we have three instructions. The first one zeros ECX. The next one moves 11 in binary into EDX. And then we subtract. We subtract the number 11 in binary from 0. If we put it in a table, it looks somehow like this. We have the number 0, which is inside ECX. ECX is the first row. And then in the second row, we have EDX, which is 11 in binary. And we want to subtract. We actually can't subtract 11 from 0. That is impossible. So we add 1 in the beginning. This is some kind of imaginary 1 that we use in order to be able to do the subtraction. When we have this 1, we can actually subtract and we get this result, which is actually going to be the result inside ECX after we invoke this instruction, the sub instruction. This time, the carry flag is going to be the borrow. We borrowed from some imaginary bit. If there was no borrow, the carry flag would be just 0. But this time we have this borrow, and the carry flag is set to be this number. It is set to be 1. In other cases, where no borrow occurs, for example in subtraction, or maybe if we add two numbers and no wraparound occurs, the carry flag is just cleared. The carry flag actually gives you information in any case. It gives you information if something went wrong. If something went wrong, for example with your unsigned addition or subtraction, the carry flag is going to be 1. But if everything went okay, then the carry flag is going to be 0. Let's look at some examples. First, we have this example. We set EAX to be of value F0, and then ECX to be of value 35 in hexadecimal. And then we add those two numbers. We get that the result is going to be 125 in base 16. Of course, we don't have wraparound here, because EAX and ECX are of very large capacity. They can hold 32 bits, and those numbers are pretty small. This number is only of size 8 bits, this is 8 bits, and the result is 9 bits. We don't actually have any problem here with unsigned addition. So the carry flag tells us that we don't have any problem. It tells us this by being 0. Let's look at another example. This time, we have the same values inside EAX and ECX, but this time we subtract. We subtract EAX minus ECX. The result is going to be BB in base 16. And again, no wraparound has occurred. The result of this subtraction is pretty usual. We just did F0 minus 32, and this was the result. So again, the carry flag is 0. Let's look at a bit of a different example. Again, we put the same values inside EAX and ECX, but this time we add AL and CL. I remind you that earlier when we did this kind of addition, we had that the addition of this number of size 8 bits and this number of size 8 bits resulted in a number of size 9 bits, which could fit inside EAX. However, this time we add those two numbers, AL and CL, and I remind you that AL, which should hold the result, can only hold 8 bits. So the result is going to be AL equals 25 in base 16. The one that we have here has no room inside AL. So it actually goes inside the carry flag. And this time the carry flag tells us that some kind of overflow has occurred when we added those two numbers. It tells us about the problem. Let's look at another example, this time with subtraction. Again, we put in those two usual numbers, F0 and 35, inside EAX and ECX. But this time we do something a bit different. We subtract AL from CL. We actually do CL minus AL. We actually do 35 minus F0. I remind you that F0 is larger than 35. The result that we get is 45. If you're not sure how it works, you can maybe review what we know about binary numbers and subtraction of binary numbers. You can even check this in your calculator, that this is the result you get. This is the result that you get from a wraparound. Actually, we can imagine that if we add this value, 45, to F0, then we are going to have the result of 35 after a wraparound. This is just a simple idea of what this borrow means in the subtraction. So this time we subtracted this number. We subtracted 35 minus F0. And in order to do this subtraction, we have to use borrow. We have to borrow from the higher bits. This is not a usual subtraction. This is subtraction with borrow from some imaginary place. So the carry flag is going to be 1, because there is wraparound in this example.